Earlier in this unit, we talked about the radius of convergence, and we said that at that point in time, we weren't really going to be able to conclude the full interval of convergence solely because we didn't have enough knowledge of all of the tests for convergence or divergence in order to be able to assess every possible endpoint. So now that we have learned all of the convergence tests that we are going to learn in this class, we can talk about the interval of convergence. So the way that this works is really similar to how we did it when we were solely talking about the radius of convergence. What we're going to do is we're going to first perform the ratio test to determine the R value that we need to make the absolute value of that R value less than 1 in order for it to converge. Then we actually need to check each of the endpoints. Meaning, let's say that you ended up with -2 is less than x is less than 4 as your interval of convergence. What you're actually going to have to do is plug x equals -2 and plug x equals -4 in, each creating their own unique series, and you're going to have to test those unique series for convergence. If this series converges, there will be a line underneath this inequality, and if it doesn't, there won't be a line underneath it. You have to check. That is a part of finding the interval of convergence, is testing the endpoints. So let's go ahead and look at some examples. Go ahead and pause the video and perform the ratio test on this example series up top. And here we have that work. That should give us that we need the absolute value of x minus 5 to be less than 1. Sorry, x minus 5 divided by 3. If we solve that inequality, we're going to end up with positive 2 is less than x is less than 8. So now all of that was review. Here comes the new part. The new part is that we not actually need to check our endpoints. So check x equals 2. So what I'm going to do is I'm going to plug x equals 2 into this series over here. That's going to give me a new series. The series from n equals 1 to infinity of 2 minus 5 is -3. So -3 to the n over n times 3 to the n. And what you should notice is that this -3 to the n in the numerator and the 3 to the n in the denominator, those are going to simplify. That's going to just become -1 to the power of n. So this series is equal to -1 to the power of n over n. And that series, we know, converges because it is the alternating harmonic series. And you don't have to show any proof for that. You can just say that it converges because it's the alternating harmonic series. So I'm going to add an or equal to the side where there is a 2. It is allowed to be 2. 2 is now within this interval of convergence because if x is equal to 2, we get a series that converges. Now I need to check what happens if x is equal to 8. Well, that's going to give me the sum from n equals 1 to infinity of 8 minus 5, which is 3 to the n over n times 3 to the n. Those are going to divide. So the series from n equals 1 to infinity of 1 over n, we know that this diverges because it's the harmonic series. So there will not be an or equal to with the 8. This is now our full interval of convergence. So we're just building slightly on to what we have talked about in previous sections by checking each of those endpoints. So what we're going to do now is we're actually going to look at, we're not going to do all 4 of our elementary series. We're just going to do sine of x and e to the x. I think that will be plenty, and I actually encourage you to later go back and do cosine and natural log, but for purposes of time, we're just going to do sine and e. So let's go ahead and write this series for sine out. Hopefully you remember this, and I'm going to move this paper and zoom in a bit. So here's our series for sine. We're going to perform the ratio test. So I'm going to say by the ratio test, I'm going to look at the limit as n approaches infinity of the absolute value. And because I'm looking at the absolute value, I don't care about the alternating piece. And I'm going to multiply that by the reciprocal of the original general term, again without that alternating piece. I'm going to go ahead and simplify that. And there it is, simplified. This limit as n approaches infinity, the denominator is going to infinity and the numerator is staying constant. So this is going to be equal to 0. And 0 is less than 1. That actually means that this series always converges. So we can say the interval of convergence is actually all real numbers, which you could use interval notation or the fancy capital R for real numbers. The cosine, which we're not going to do, the cosine interval of convergence ends up being exactly the same. But I do encourage you to try that one on your own and make sure that you can work through the ratio test. So remember, it won't be all real numbers if this portion right here still has an x in it that we need to then bind as we did in the example above. Let's go ahead and look at e to the x. So here's our series for e. We're going to say by the ratio test, the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n in absolute value, which is sort of irrelevant on this particular problem. Actually, you know what? It's not irrelevant because our x's. So those are going to divide out. So we're going to be left with x to the n over n plus 1. That limit is also equal to 0, which is less than 1, which means this series converges everywhere. I do encourage you to do natural log on your own. I will tell you that the answer, natural log, actually doesn't converge everywhere. It converges between 0 and 2. And you're going to see when you check the endpoints that it does actually converge when x is equal to 2 because we end up with the alternating harmonic series. And it doesn't converge when x is equal to 0 because it's just the negative version of the harmonic series, which is not alternating and therefore also diverges. All right, let's look at some more concrete examples, some less elementary series and more just different variations of series, and figure out what their exact interval of convergences are, including checking of the endpoints. All right, number 5, the limit as n approaches infinity, and I like to put by the ratio test up top, of the absolute value of x minus 3 to the n plus 1 over n plus 1 times n over x minus 3 to the power of n. A bunch of things are going to simplify here. The limit as n approaches infinity of the absolute value of x minus 3 times n over n plus 1. Well, the limit that's happening with the n's is going to be 1, so that's going to just leave us with the absolute value of x minus 3, which we need to be less than 1. So negative 1 is less than x minus 3 is less than 1. Add 3 everywhere, and we have our interval. But before we can say that this is the answer, we need to check the endpoints. So I'm going to actually come down and take up some space down here to do so. So I'm going to check x equals 2. If I plug in 2, the series from n equals 1 to infinity of negative 1 to the n over n, this is the alternating harmonic series. I love it when that happens, which we know converges. So this is going to have a line underneath it. And then we can check what happens when x equals 4. We're going to get, I think, the regular harmonic series. You may have guessed 4 minus 3 is 1. 1 to the n is just 1, which diverges because it's the harmonic series. So I'm going to rewrite my interval over here. Our final interval of convergence looks like this. Why don't you go ahead and pause the video and see if you can do number 6 on your own. So here's the work for the ratio test. Now go ahead and check what happens when x equals negative 1/3 and what happens when x equals positive 1/3. So when x is equal to negative 1/3, the numerator is going to end up simplifying to just be positive 1. So we have the sum from n equals 0 to infinity of 1 over the square root of n plus 1. We're going to use a comparison test. I'm thinking that probably diverges, considering it looks a lot like a p-series. So we know that the p-series of 1 over the square root of n diverges, since p is equal to 1/2. And then we can do the limit comparison test, the limit as n approaches infinity of 1 over the square root of n plus 1 times the square root of n over 1. And that limit is going to be equal to 1, which is greater than 0. Therefore, it diverges by the limit comparison test. So no or equal to sign with our negative 1/3. Now let's look at what happens when it's positive 1/3. So if n is equal to positive 1/3, the numerator is going to become negative 1 to the power of n, which is alternating. So my gut is telling me to check the alternating series test. I can tell without actually doing the work, I know I do need to do the work, but I can tell that that limit is going to be equal to 0. The denominator is going to be getting bigger, so 1 over, if I plug in n plus 1, that would give me n plus 2, is going to be less than or equal to 1 over the square root of n plus 1, so a sub n plus 1, less than or equal to a sub n. Therefore, this converges by the alternating series test. So our final interval is going to have a less than or equal sign, a less than or equal to sign with our positive 1/3, but not with our negative 1/3. So pause the video, make sure you got that. Yeah, there is a little extra work because you're basically doing a bunch of tests all in one problem. In this one problem, number 6, we did the ratio test, we did a comparison test or a limit comparison test with a p-series, we did alternating series tests, so lots of different convergence tests all in this one problem just to finalize the interval of convergence. These problems can be time-consuming. Let's go ahead and look at number 7. So step 1, perform the ratio test. Once we've performed the ratio test, we're going to set what we get here, absolute value of x. We need that to be less than 1. And that's a pretty easy one to solve. We know that that means that the base for our interval of convergence is -1 to +1. But what we need to do now is check the endpoints. We need to see what happens when x is +1 and what happens when x is -1. So let's go ahead and look at -1 first. If x equals -1, this series becomes -1 to the n over 2n minus 1. And this is an alternating series, which makes me assume my first gut is to try the alternating series test. So the limit as n approaches infinity of 1 over 2n minus 1 is 0. 1 over, if I do direct substitution and put n plus 1 in for n, this is definitely going to be smaller since the denominator will be bigger. So a sub n plus 1 is less than or equal to a sub n. So I've shown both requirements for AST. Therefore, this converges by AST. So there will be a line underneath the inequality there. Now I'm going to see what happens when x is equal to 1. So let x equal 1. So this becomes the sum from n equals 1 to infinity. 1 to the n is just going to be 1. So 1 over 2n minus 1. This looks a lot like 1 over n. I kind of have a feeling that this is going to diverge, but to be sure, I need to use a comparison test. So I'm going to compare to the sum from n equals 1 to infinity of 1 over n, which diverges because it's the harmonic series. Don't have to prove that, I can just show it. I can't use the direct comparison test here because my terms won't be smaller the way I need them to be. 1 over 2n minus 1 is going to be smaller than 1 over n, which means in order to use a comparison test, I need to use the limit comparison test. So the limit as n approaches infinity of 1 over 2n minus 1 divided by 1 over n. This limit is going to be 1, which is greater than 0. Therefore, it's going to diverge by the limit comparison test. So my final interval of convergence is going to be right here. Since number 10 is right there and easy to see, why don't you go ahead and pause the video and see if you can get all the way through number 10 on your own, including checking those endpoints. So what you're going to see happen on 10, by the ratio test, we're going to get that our interval of convergence is -4 less than x less than 4. Both endpoints, when you check them, end up converging. -4 is going to converge by AST. +4 is going to converge by the p-series test. So we actually have a fully, not that you have to use interval notation, but a fully bounded interval including both of the endpoints. All right, let's look at the last two problems, 8 and 9. and work through just 2 more practice problems before we wrap up this lesson. I'm going to encourage you to do both 8 and 9 on your own, and then unpause the video and I will work through them mostly step by step. Okay, so step 1, I'm going to start with 8, the ratio test. So I'm going to quickly perform the ratio test. Once I'm done performing the ratio test, I am here. And now I'm going to rewrite the series letting x equal -1 and seeing if that converges first, and then if x equals +1 and seeing if that converges. So something I want you to note about x equals -1, this numerator, this series could just simply be rewritten as 1 in the numerator. It's going to become -1 to the 2n, which is always going to be positive, and I can rewrite the denominator as n to the power of 1/3, which makes this a p series. 1/3 is less than 1, therefore this diverges by the p series test. Now I'm going to go ahead and look at what happens when x equals +1. This series could be rewritten. The +1 to the n becomes irrelevant, so -1 to the n over the cube root of n. This series is alternating, so I'm going to check the alternating series test. The limit is 0. 1 over the cube root of n plus 1 is less than or equal to 1 over the cube root of n, so a sub n plus 1 less than or equal to a sub n, so I've met my 2 requirements. This converges by AST. So I'm going to have an or equal to only with my +1, and now I have wrapped up my interval of convergence. Last problem. Step 1, ratio test. So that will get me here with my interval of convergence, and then I need to check each of those endpoints, starting with x equals -1/2 and plugging that into the series. And I just noticed this series isn't defined when n equals 0, so do me a favor and go up here and change this to be an n equals 1 so that this series actually does exist over all of its terms. So I'm going to change this to a 1 as well. -2 to the n times -1/2 to the n, that numerator is just going to become 1 to the n. So this is going to simplify to be 1 over n squared. That's a p series. 2 is greater than 1, therefore this converges by the p series test. So there is going to be an or equal to here. Now let's go ahead and check when x is +1/2. Here, the numerator is going to simplify to be -1 to the n over n squared, so my gut is going to tell me to check the alternating series test first. The limit as n approaches infinity of 1 over n squared is equal to 0. 1 over n plus 1 quantity squared is going to be less than or equal to 1 over n squared, so a sub n plus 1 less than or equal to a sub n. So this converges by AST as well. So another interval of convergence where both endpoints are included. So big idea with finding the interval of convergence for a power series. Always start with the ratio test to find the interval of convergence numerically, like what the numbers are going to be at the endpoints, and then plug in the endpoints and actually check to see if each endpoint is included. Lots of work could potentially happen there using different tests to check each of those endpoints, but that's what makes these problems really a great practice of a lot of different things at one time. So write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.